MS Ramaiah University of Applied Sciences.
Hello students, in this session of Control System Lab videos, we are going to study how to design a PID controller. First, let us open a new script. So in this window, we are going to type the program to design a PID controller. Let us first define the transfer function. The transfer function numerator has the coefficients 1. The denominator has the coefficients 1, 3 and 1. Let me define the transfer function as GP, which is given by transfer function of numerator comma denominator. Let me save this script. I will give the name as example. I will run the script. So this is my transfer function, which is 1 by s square plus 3s plus 1. Let me now analyze the step response of this transfer function. The command is given by step of GP. Run. So this is the step response for the open loop transfer function. Now let me consider a closed loop transfer function. I will convert this transfer function GP into closed loop transfer function by inserting a feedback element with a gain 1. Now I will define a closed loop transfer function M, which is given by feedback of GP comma H. Let me run this. So this is the closed loop transfer function. It is similar to the open loop transfer function, except in the denominator we have 3s plus 2 instead of 3s plus 1. Now let me analyze the step response of this closed loop transfer function. Step of M. So this is the step response of the closed loop transfer function. Let me introduce a grid. The command is grid on. I will also. So this is the step response for the closed loop transfer function. You observe that the step response reaches a value of 0.5 at approximately 6 seconds. I will also type hold on so that it remains, the graph remains even if I plot other graphs in future. So when I click or type double % symbol, it opens a new subscript inside the script which will not affect the main script. So I'll type the values of the PID controller: proportional gain KP, integral gain KI and derivative gain KD. Let me define the transfer function of the PID controller GC as PID of KP, KI, KD. So by introducing a PID controller, I want to improve the step response of the given transfer function. So let me define the closed loop transfer function, which includes the PID controller, which is given by feedback. First I will write the forward path transfer function, which is GC into GP, and the feedback path transfer function, which is H. Let me run. So this is the step response of the closed loop transfer function, and MC is given by 1 by s square plus 3s plus 2, which is same as the closed loop transfer function without PID controller, as my proportional gain is still 1. Now let us analyze the step response of MC. MC stands for gain with controller, which will be the same because the proportional gain is still 1. Let me close this. Now what I will do is I will go on increasing the value of proportional gain. Right click, increment value and run selection. So what this will do is, as I press on the plus symbol, the proportional gain is increased by 1 and the step response is plotted. So as you can see, the step response, the final steady state value has increased. Let me switch on the grid so that we can have a better view. Grid on. I'll also type hold on. Let me run. As you can see, this was the initial plot, and as I increased the proportional gain, the steady state value increased. So let me further increase the proportional gain. So select and increase. So as you can see that as I go on increasing the proportional gain, the steady state value goes on increasing. Let me rearrange these windows so that we can have a better view. So as you see, as I go on increasing the proportional gain, the steady state value goes on increasing, also with a reduction in the rise time. So these are the steady state values. Initially it was 0.5, then it increased to 0.66, then 0.75, 0.8 and 0.833. So as I go on increasing the proportional gain, the steady state value goes on increasing. So this is my final plot. Let me close this and I will run the script. So this was the initial step response of the closed loop transfer function, and this is the step response with PID control, with proportional control. The steady state value is still not 1, it is 0.9, and we have a small peak overshoot, and then the response settles down at around 4 seconds. Now I will introduce a derivative controller. Right click, increment value and run selection. So let me arrange the windows. As I click the plus button, you see that as I increase the derivative gain, the peak overshoot reduces and the rise time also reduces. So you observe that the peak overshoot has reduced and the rise time has decreased substantially. Let me close this. Now let me run. So initially I had a plot like this, and now with proportional and derivative control I have a plot like this. So this is the final value. So as I increase the derivative gain, the rise time decreases and the peak overshoot reduces. Let me introduce an integral gain and see what happens. Select this, right click and select increment value and run section. As I click on the plus button, you observe that the steady state value increases and reaches 1. That is, there is no steady state error if I introduce an integral gain. As I go on increasing the integral gain, the steady state value improves with a slight peak overshoot. Let me run this script. So as you can see, initial plot and the present plot with a slight peak overshoot. To reduce the peak overshoot, I will increase the derivative gain. So when I increase the derivative gain, the peak overshoot reduces. So let me select the derivative gain and increase it. So as you see, when I increase the derivative gain, the peak overshoot reduces. So as I go on increasing the derivative gain, peak overshoot reduces. I'll also slightly increase the proportional gain so as to get a proper step response. Let me close this and run the script. So initially I had a step response like this, and now I have a step response like this after tuning the PID controller. So by using a PID controller, we can improve the step response of any given system. So this is the final closed loop transfer function with the PID controller, and these are the tuned PID values. Thank you.
At MSR UAS, we spark your imagination unlike any other.